Hello everyone, and welcome to a little presentation in which we are going to derive a wonderful set of equations that we can use to describe uniformly accelerated motion. Now we're going to do these derivations by looking at the graphs that we've already developed for uniformly accelerated motion. For example, here is a velocity time graph. Okay, we know that for uniformly accelerated motion it would look like a straight line, a linear graph with a slope of the acceleration, and a y-intercept which represents the initial velocity. So as we did back in the lab extension, we can create a math model out of this linear velocity time graph. The y variable is, of course, the final velocity. And that equals the slope, which again is the acceleration, the x variable, the time, plus the y-intercept, which is the initial velocity. And as I mentioned to you back then, if you were to look this up in the book I never gave you, addition is commutative, so we can switch the order, and we get our first equation that describes uniformly accelerated motion. This equation says that the final velocity is equal to your initial velocity plus your acceleration times your time. Now remember that acceleration is simply the rate of change of velocity, so when you multiply that by the time, you get how much your velocity changes. If you add that to the velocity you start with, you end up with your velocity at the end. Now, as we've talked about a little bit in this unit, and we've done kind of extensively on the last worksheet, we needn't confine ourselves to only analyzing slope and y-intercept on velocity time graphs. We could also look at the area under the curve. For example, let's say we let an object move for a time we will call t, at which point, according to the graph, it will be going at a velocity we will call v. Then we could look at the area under the curve here. Now this one's a little more complex, right? It's kind of hard to figure out. It's not just one shape, but if we drop a little horizontal line in right here, notice that we can break it up into a rectangle and a triangle. So we can find the total amount of area by finding the area of the rectangle and adding it to the area of the triangle. No calculus needed for that. Now this is a graph of velocity versus time, so hopefully you remember here that the area under the curve is simply the displacement, final minus initial position, or the change in position. The area of a rectangle is, of course, length times width, so I'm just going to do the dimensions in the order I have them in my PowerPoint here. So this dimension of our green rectangle is the initial velocity. This dimension is the time. So that's the area of the rectangle. The area of the red triangle is 1/2 base times height. The base here is a time t. The height we have to talk about a little bit, because I don't actually want the height from 0 all the way up there, because that's not the triangle. I want the height from here to here. So what is this height? Hopefully you can see by looking over here that the height here would be the final velocity minus the initial velocity, or if you will, the change in the velocity. Right? This is how much your velocity changes during this part. So 1/2 base of t and a height of final minus initial velocity. So again, we get this just from the area under the curve of the velocity time graph. Now we can make this a little simpler, do some simplification here. First of all, let's distribute through the 1/2 and the t. We get displacement is equal to initial velocity times the time plus 1/2 the final velocity times the time minus 1/2 the initial velocity times the time. By the way, feel free to go back and use the rewind button if you need to slow me down. Now we do have a couple of like terms we can combine on the right hand side, there and there. The final velocity times the time and a minus 1/2, sorry, that's the initial velocity times the time, and over here we have a minus 1/2 the initial velocity times the time. So if we combine those two together, we get 1/2 the initial velocity times the time. Notice the 1/2 final velocity times the time just gets carried along. And now to make it look like the equation as it's traditionally written, each one of these terms on the right has a 1/2, so I can factor it out. And each one of these terms on the right has a time, so I can factor that out as well. And I come up with what we are going to call our second equation of uniformly accelerated motion. It says the displacement is equal to 1/2 times the quantity final plus initial velocity times the time. Now look closely at this equation and you may see kind of where this equation comes from. Consider, what is final plus initial velocity divided by 2? 1/2 times this quantity. Right? What is that? Well, if you take the velocity you end up with and you add the velocity you started with and you divide by 2, that should be your middle velocity. Right? And since you're uniformly accelerating, you're smoothly increasing your velocity from VO to V, that middle velocity is in fact your average velocity. So in fact, this equation is basically saying displacement is equal to average velocity times time. In other words, it's not really a new equation at all. It's just a new way of looking at it. Now, why do we even need a second equation? I mean, why isn't this equation good enough? Because notice it has different quantities. This one, the original one, relates the final to the initial velocity, the acceleration, and the time. This one relates the displacement, your change in position, to final plus initial velocity and the time. And so a whole different set of variables there. Now traditionally there's a third way of looking at this, but it's going to start out the same way as the second equation. We're going to look at the area under the curve. So again, the area of the rectangle plus the area of the triangle. And just going through this all at once, it's the same thing as we did before. We have the area under the curve is the displacement. The area of the rectangle is the initial velocity times the time. The area of the triangle is 1/2 a base of t and a height of final minus initial velocity. But rather than just manipulate this right-hand side like we did a moment ago, let's consider the original equation. Now, for reasons which will become apparent in a moment, subtract the initial velocity from both sides. In other words, move the initial velocity over to the left. This gives us final velocity minus the initial velocity equals the acceleration times the time. In other words, the change in the velocity is the acceleration times the time. And here we have the change in the velocity. So we can make a substitution. This gives us an equation that says displacement is equal to the initial velocity times the time plus 1/2 the time times the acceleration times the time. Multiply through, times time is time squared, and you get the third equation, which says that the displacement that you go is equal to your initial velocity times your time plus 1/2 the acceleration times the time squared. Now hopefully this equation looks familiar, because we had a version of this back when we did the lab extension where our initial velocity was 0. And notice if your initial velocity is 0, 0 times the time is 0, and we get displacement is 1/2 acceleration times the time. You remember in the original lab where we said position was proportional to time squared and the slope was 1/2 the acceleration? Here it is again, just in a more general version. In a version where your initial velocity doesn't necessarily have to be 0. So in other words, the 1/2 acceleration times time squared tells you how far you go because you're accelerating. The initial velocity times the time tells you how far you went because you were already moving initially, and you add those two up, and that's your total change in position. Again, this is a third equation. Why do we need a third? Because look carefully and notice that each one of the three equations is lacking one of our variables. Our first equation has nothing to do with the displacement. Our second equation has nothing to do with our acceleration. And our third equation has nothing to do with the final velocity. So if you don't know your final velocity, you can relate all the other variables with this equation. This is going to make this handy so that we don't have to use as many equations or solve one and plug it into the other. We can just solve a single equation for what it is we're looking for. So we now have three equations. And these three equations have a special name. Since they are the equations of uniformly accelerated motion, they are known as the kinematic equations. And since they all came from, going back here, a linear velocity time graph, they are only true if we have uniformly accelerated motion. If your acceleration is changing, you can't use these equations. So here's our three equations in the order that we derived them. Now you might notice this hole here. That's because traditionally there is a fourth equation. The fourth equation relates the final velocity to the displacement, okay, and doesn't have the time as one of the things you need to know. So notice the time is in the first three equations. So there's a fourth equation that doesn't have time but relates final velocity to displacement. Now tomorrow I'm going to do an activity